Hey guys, how's it going? Welcome to the channel. So today actually I want to cover one of the most underrated topics I feel like in machine learning, which is efficient uh, machine learning and deep learning. So I feel like a lot of research and investment has been actually invested into getting state of the art. We can see recently with models such as GP3. We can see with diffusion models, Dino from Facebook. All of these models probably have one thing in common. They have a lot of parameters, right? Which makes it difficult for us to actually deploy them in production, right? So if we're thinking from a software engineering perspective, so we know that from a software engineering, we usually care about things such as latency, we care about throughput, right? These are the important things because we want to make sure that we maximize users experience, so the app should be fast and responsive. So we don't want a model to kind of like slow our application down. For example, let's say you have a facial recognition app, right? It's working on a mobile device. So we should know all the compute that is on the mobile device as we're designing our model. So having a model with something like weights that are something like maybe 500 megabyte, this is gonna become hard to use this on the mobile device. So this is what the talk of today is gonna all be about. All the techniques that have been introduced and all the researchers that have introduced some of the cool techniques and how we can overcome this problem. So I feel like Microsoft is one of the companies that try to kind of like capture all the important concept. I'm just going to show you this diagram that is coming from DeepSpeed introduced by Microsoft. So what you're seeing here is that they try to capture all the important components which enable us to have an efficient machine learning. We're going to cover this as we go on. Please note that this is going to be a series whereby we're going to build efficient machine learning models as we go on, and I'll be showing you how we can actually deploy them in like a mobile device, something like that. So we can think of this as an introduction to these concepts. We're going to go into detail in each of the component as we go on. So what Microsoft did was that they created the library called DeepSpeed, whereby they try to capture all the important components to enable us to have an efficient ML. So we can see that they have a neural architecture, they have distillation. We're going to talk about these, pruning, quantization, and obviously I don't think they mentioned here, but also when you're training, you have things such as model parallelization and data parallelization. They have inference engine. Inference is quite an important component, especially around the compute that you choose. It's gonna determine how fast the application is gonna be when you deploy your model. So we're gonna cover this. Another researcher that I personally follow a lot is Song Han, which is one of the most known researcher in the efficient ML space. He also tried to create a diagram whereby he tried to show how using a technique with pruning and quantization can actually reduce the number of weights by 10x. So, which is quite cool. So the reason I'm showing you this is that I've seen a lot of people who try to bring all of these important concepts that we're going to cover into one library. Which I find quite cool because now people can like use one thing to kind of like create efficient machine learning model. This include inferences and stuff like that. Before we kind of like dive deeper into efficient deep learning, so I thought I should give credit to Naresh, who went and created this PDF that we're looking at, and Garaf. So all the techniques that we just spoke about, pruning, quantization, they all boils down to we try to have efficient training and efficient inference. So I'll try to categorize everything into these two. So for instance, you could have heard that training machine learning could take days and more hours or months, something like that, especially if you're training GP3 models. And this could be costly, especially given the how training on cloud is very expensive. So we're going to talk about techniques such as model parallelization, data parallelization, which have been introduced in recent research, and how they help us to speed up the training. And all of this boils down to having problems such as, does the model fit in memory? Especially if you have a model that is very huge, it might not even fit in one server. So how do we then distribute the model into different servers? All of this problem, we're going to get into them into more details. So with the inference portion of things, we can think of this as we might want to make inference with a model. Let's say our target is to make prediction within like 1.5 milliseconds, but the model that we have is probably taking something like 100 milliseconds, which is bad. So how do we then reduce that latency that we might be having? Okay. However, with all of this optimization that we might have to reduce latency and probably like have efficient training, there is always some sort of like trade-off associated with these optimizations that we try to make. And so what happened is that if you try to decrease your inference, usually it comes at the cost of accuracy. I don't know if you have seen like a lot of research papers. What researchers will do is that they will have an accuracy, probably they will have an inference time. So how they compare, and they know that their model that they've just built is quite efficient. They have this curve. So current models will probably be here, which makes sense because you try to minimize your inference at the same time you try to get the highest accuracy. So the best model is probably going to be somewhere here. So what we call this Pareto optimal models. So hence in the research papers, you'll see some sort of like when the researchers compare their model, they'll have some sort of like something like this to show that it's efficient. When it comes to inference, it's efficient and the accuracy is high, which means that the model is good. So, but what I'm trying to raise here is that usually when you try to reduce your inference, it might come with a little cost on the accuracy side of things. So we need to find the best trade-off so that like we can have an efficient models. Okay. So I'm just going to jump and go into the mental model of efficient deep learning. So I feel like I said just now, that usually try to get a better accuracy. It comes at the cost of like model size, latency. So there is definitely a trade-off. So if you probably compress your model, you may want to make it maybe small, maybe it was very large so that it can fit in a specific device. You probably gonna then have to reduce the accuracy of the model by a little. But I've seen a lot of techniques, especially with pruning, whereby you can prune literally 90% of the weights and still maintain the same accuracy or even slightly better model. That's how advanced some of these techniques have gotten in the recent days. So but that's the point for the most part, is that usually when you apply these compression techniques, they usually come at the cost at trading accuracy, because you're reducing those weights that you land in the when you were training your model. Okay, so I like what the researchers have done, or the people who read the paper, is that they've kind of like divided this into four, whereby we have compression techniques, we have learning techniques, we have automation technique, and efficient architecture, which we're going to cover in more details in this session. So the first one we're going to look at is compression techniques. So the first compression technique is the quantization. So you can think of quantization in simple terms is that we try to map high precision domain to quantized domain. So think of it as we're moving from 32-bit probably to something like 8-bit. A better perspective, let's think of like we have a weight. I'm just gonna, weight is always a matrix. So we have weights something like around this way. So we can say 4 times 4, which is going to give us 16. Then we can multiply this by 32-bit, and we can probably divide this by 8, which is going to give us 64. So this is 32-bit. So what if now we decide to move to 8-bit? So if we move to 8-bit, this calculation will remain the same. We're going to take the 16 parameter for our weights, and we're going to multiply it by 8, and we divide it by 8. So which is going to give us something around 16. So you can see how reducing the bit, it helps us to reduce the number of params. That's the significance of also using the quantization. But I want to raise that quantization can also come at the cost of, it requires a specific computation, so which we're gonna touch when we get to the infrastructure portion. But just keep that in mind for now. So our second topic is pruning. So pruning, you can think of it as we try to remove redundancy in our network. Especially you can think of like some of the networks, they have redundancy. So they hold the same information, especially in DeepNN or CNN, there's a lot of redundancy. So we can remove some of the connections called synapses or neurons, and without actually losing accuracy at all. I'm gonna show you guys from a practical standpoint. We train a model which we pruned by, meaning that we removed some of the parameters by 90%, and we're still able to maintain the same accuracy as a very dense model, right? So these type of models, we call them sparsity. They also require specific specialized compute to run on inference. So, but this is another technique that you should keep in mind. Okay, so we looking at the learning techniques, which is apparently my favorite topic. So we have the first learning technique is called distillation. So the distillation, you can think of it as we have a smaller model that is deployed, and when we train this smaller model, we train it with a very huge model, very dense model, which is going to help this student model that we see here. So essentially what's happening is that if we're going to have like labels, which the small model will have to make predictions on, and also like the teacher will have to make predictions on this. Then this model will have to learn from the teacher and also from the training data. So which means that it's going to have two loss functions. Then we're going to do a propagation to the model using the gradient from the distillation loss and the cross-entropy loss. So you might be asking yourself, why are we doing this? So we want to help the model to be able to learn. Mostly importantly is because we want to be able to say, okay, if the model predicts something like a car and the output was supposed to be a truck, the loss here should be small, meaning that the penalizing shouldn't be hard. So whereas if like it was supposed to, it predicted something like banana instead of a truck, the loss will be high. So training the model like this, we're able to get a very powerful model. You can look at models such as Distillation, which is still quite powerful, but it's very small. So check it out on Hugging Face. But that's the point. We try to use this complex model that we have here. We train it by the output here. We're just gonna see if like it can get it right. Yeah, and if it get it wrong, then we penalize it. We propagate the gradient here. Okay, cool. So the second learning technique that we look at is the data augmentation. So you can think of data augmentation as like we try to generate a different variety of data. For example, let's say we're given an image of a dog. We could probably, what we can do is that we can rotate this image. That's another technique that we can do, is that we can crop it or something like that. So we generate a variety of the data of images from the same image. So this way we make the model learn more, because it can learn that, okay, this is a dog, these are all the properties. It can learn from all the dimensions, because even if we turn the image, we crop it, it's still going to be able to classify it as dog. So that's the second learning that we have. Now let's look at automation. Automation is probably one of the techniques that I pretty much find to be cool, given based on the research that I've read, like a lot of human interventions, especially when we're training, especially if we pass the parameters manually, the training can take some time. So we need to come up with like some sort of like smart automated way to generate the parameters as we're training. And one of the example is automated hyperparameter optimization, which is the technique. Like I said, it's actually there to kind of like replace manual tweaking of hyperparameters. This could mean like changing things such as learning rate or dropout manually, with the hopes that you're gonna increase the accuracy. Especially if you're using a scikit-learn library, there's a function called random search, which randomly search for hyperparameters and try to find which ones are doing good. But the point that I'm raising here is that using these manual tweaking and random search, this can actually increase the training time. At the same time, you can not get the best accuracy, because you just like try to guesswork the parameters, learning rate and stuff like that. So what the current techniques we have is the techniques such as Bayesian optimization. So you can think of it as an algorithm that try to find the best parameters in an efficient way. So I think if we can look at this visualization, it can probably make sense. So we can see that all of these red, it's whereby the loss is high. So it's not gonna try to play there. It's gonna try to play where this on this point, because this is where we have a high accuracy. So the point here is that the model does not play on parameters whereby it's gonna get off. It plays on parameters whereby it's gonna get high accuracy. So it's very efficient, and it can actually reduce the training time, because it does not have to look at the large space of parameters to search to find the optimal accuracy. Okay, so neural search has been getting a lot of attention recently. So you can think of it as we try to build efficient architectures by using this by searching for parameters, the building blocks, rather, not the parameters, but building blocks such as layers. And as we search these parameters, these parameters are going to get us a lot of accuracy or efficient model. So we can optimize it that way. So how it works is that we have a controller which is composed of the search space and search algorithm state. So this is a trial and error a routine whereby we search for the parameters or the building blocks to build our network. So what we do is that after we found all the parameters, it could be layers, it could be, if it's a convolutional layer, all of this, right? Then we train the model, we get the feedback. Then after we get the feedback, we go and look for more efficient architectures than with this search algorithm. Then we go and evaluate the model. So it just keep on doing that. But the point here is that we build efficient architectures for deep learning. So have you realized that instead of like manually thinking that, okay, I'm just gonna create a convolutional layer with input or output channel of 564 or something like that, this neural search architecture help us to do that while it's maintain high accuracy or efficient network. All of these concepts, I know that I'm explaining them at the high level. We're gonna get into too much detail into them as we're gonna get into the coding part and how they work. So I think you can take this as an introduction. Okay. Sometimes I think like it's also important to start from efficient model architecture instead of like training a very complex model. Then you try to apply the techniques that we spoke about. How about you start from a very efficient model? For example, let's think about attention. I don't know if you guys know attention model, but probably most of you guys know. So it has a quadratic time space, right? Recently, I've been looking at papers by the guys at DeepMind, whereby they introduced a performer which can run at a linear time, right? So also I think it is Microsoft who introduced I'm not sure, but I think it's Microsoft. They introduced the fast former, which is also a linear time model. So these models here, they are efficient than the original attention transformer model, which was introduced in 2017, which runs in the quadratic time. So using models such as performer, you can check the papers, guys. I'll leave the link. You can read these architectures, performer, fast former, which are efficient. You can read more about them. So another techniques that is being used, let me just spread my window. So another technique that is used is called separable convolutions. So which actually help us to have efficient convolutional neural networks. So the first one that you can think of is the spatial separable, which actually help us to separate the kernel into two. So spatial separable, you can think of it as we have an image, right? Which is, we can think of it as 7 by 7. So what happens is that all the time we usually multiply this by some sort of like a kernel. So instead of having a tray by tray, kernel, what we do is that we multiply the image by a tray by a 1 by tray kernel. So we're gonna have something like that. Then we get the intermediate result, right? Then we multiply this, because we're supposed to have a tray by tray. We're gonna have something like this time is gonna be tray by 1, something like this, right? So the significance of us doing this is that if you try to count the parameters in like 1 by tray and 3 by tray, you're gonna get 6. But if you use a 3 by tray matrix, you're gonna get 9 parameters. So that's the spatial separable. It helps us get an efficient CNN at the low cost of accuracy. However, some of these kernels are not separable sometimes. So that's the drawbacks. That's why we have another technique called a depth-wise separable technique. So you can think of this as, we're gonna just gonna scroll down, as we have an image. So we can think of our image as 7 by 7, and we have by the way, probably we have a channel. So we're going to take this image and we're gonna separate it by channels. So we're gonna have a channel here, and we're gonna have a channel here, and we're going to multiply this channel by a 3 by 1, 3 by 3 by 1, 3 by 3. So these are kernels. But the point of doing this is that we can actually reduce the number of parameters and the number of calculation required to do the matrix. Then when we are done, we add all of this into one matrix. Then the second step from here is that we do a pointwise operation. So we take this and we multiply it by a 1 by 1 convolution. So that's the technique which I'm gonna try to cover these two concepts in more detail, and we're gonna probably do a code simulation, and we're gonna see how it helps us to. But the bottom line is that these techniques that I spoke about now is that they all try to get us an efficient model. So just gonna scroll down. We have we also have like embeddings, especially in natural language processing. So embeddings are very expensive, guys. So what happened is that let's just come here. So what happened is that, let's say you have a word, right? You have some sort of like a word. I'm just gonna write something like hectare, right? So you need to embed this way, because machine learning works with numbers. So what you will do is that usually people will create a vocab, because they will take all the words that they have in their training data set. They will create a vocab to say, okay, 1 refers to hectare, and maybe it occurred, maybe they're going to have a count something like 50, right? So when we get a word like hectare, what we do is that we look it up. It's an O of 1, because we can think of this as a hash, as a dictionary. So we're gonna get that hectare there, and the integer, which is 1. Then we use this integer. We still have to look it up in the embedding table. So we're gonna have to look up another table which we call embeddings. So in this embeddings, we're gonna have 1, and it's gonna have all of these numbers that represent that name called hectare. So here we can have something like floating point, 5, 6, and up to a specific dimension number. So, but all of these, it's a space. This cost us a lot. So what happened was that if you have something like that, let's say you have something like 50,000 words, right? That means you're gonna have 50,000 embeddings that you have to look it up. So which is gonna be expensive. So what they do is that they introduce a technique called a hash function, which replace the vocab. So we don't need the vocab anymore. So which vocab, what I told you about, we're gonna remove this. So what happened is that if we're gonna get a name like hectare, then what we do is that we're gonna apply a hash function, so which you're gonna pass in the name there, right? Then this hash function is gonna give us a specific value, something like maybe 4. Then we use that 4 on our embedding tables to get a specific embedding, because we need to pass it into our deep neural network. So we're gonna have embedding table, and we can get a specific row with this 4, right? And it reduces the embeddings, reduces the number of the original embedding table by a factor of magnitude. So it's quite efficient. However, I've read a paper from Google, I think it was called deep hash embedding, which I pretty much like the idea. So what the folks does there is that they say that you don't need embedding tables at all. So especially, I feel like this is very useful. So what they say is that if you have an ID, let's say of Dre, you can think of this as a name. It's okay. So we pass it in. We have a vector here, which we can of dimension. We convert this into a vector of dimension probably 1 or 24, and this, it can be any value and it's gonna be the same, like even in production, meaning that this is determined technique. So what we do is that we pass it through our NN model, and we get the embeddings at the end of the day. So the embeddings could have a dimension of 32. Some of you might be asking, why are they doing this? Firstly, you're removing the embedding tables. There's another problem called out of vocabulary, which is a problem in like with embeddings. So especially like if you have a new word that pops up, like maybe let's say let's say something like Karabo, it's a name, so you're gonna pass it, but it's not in the embedding table, so you might get an error or something like that. So it handles out of vocab very well. It handles huge vocab size. It's dynamic in nature. So that's the advantage. I'll leave the link to the paper so that you can read about it more. And this could actually be useful, right? Especially I've read from Uber, I think it was estimating time arrival. So what they do is that they try to embed, they use a hashing, by the way, but not the deep hashing technique. So what they do is that they try to embed everything, like literally even time. So what they do is that they want to embed minutes for a week. So let's say we have, how many minutes do we have a week? And so that we can determine. So let's say we have 60 minutes per day is going to be times 24 times 7. It's going to be somewhere around 10,000. So what they do is that they try to create embedding for each and every minute, right? In that each minute is going to have its own embedding. That's what the folks at Uber did. So this type of deep hashing can be actually be useful in this type of an environment, because you don't have to create an embedding table, right? You can just pass in the minutes. Obviously, I know that, yes, it comes at the cost of having weights, but you can probably use the quantize pruning techniques to reduce the weight and compare if like having an embedding tables and having a model which is very small but it's very deterministic and well distributed, meaning it's always consistent given a specific value, then I think that way it can be useful, right? So check it out. I'll leave the paper and research. Please, for it to be deterministic, when I say deterministic, I mean given an ID like Dre, even in production, it's gonna have the same embedding. It's like using hash functions. There's certain hash functions, guys, that actually they're not deterministic, right? This thing is hash functions such as I think MD5. So you need hash functions such as farm fingerprint. So something like that, it can it's very deterministic and it's lightweight, meaning it's not expensive to calculate. So something like that. And actually with Google, they use multiple hashing functions to avoid collusion. So here there were multiple hashing functions that they used. But that was a quick crash course on how embeddings can take a lot of space and how you can actually reduce them. Yeah, we're gonna get into more techniques, recent techniques, which don't actually require embeddings. So as we go on, so infrastructure. This is like one of the most exciting fields personally that I like, because I used to like neglect infrastructure, guys, especially when it comes to training a model. A quantized model requires a specialized model, including a pruned sparsity model requires a specialized I meant to say computing resources. So it's very important to understand all of this, and especially if you're building a machine learning platform for an organization, it's very important that you understand what the inference layer, what type of computation it's using, because not every computation is going to be efficient for your model. So because they are tuned differently, I think we saw in the Microsoft image. So I think well known is the TensorFlow Lite, PyTorch Mobile. I've recently read a paper from Facebook whereby they have an AI template. They just recently uh, had this, which beat most of these inference frameworks. So it's very efficient when they compared when they did. So I'm gonna look at it and see if like that's the case. Yeah. So, but I'm not gonna jump into too much detail into the infrastructure. I was just shooting you guys that it's very important to understand all the infrastructure when you deploy your model and when you're training. I'm gonna touch it on the practical side of things. And I think we've covered pretty much everything that I wanted to hint, guys. I really appreciate you guys. If you've stayed this far, I really appreciate it. I'll definitely create more powerful. We're gonna build a mobile application, a project, and I'm gonna show you guys how all of this concept ties up together. There's so many of them. They can be used differently on different occasions, different use cases, but we'll try our best to go into more details and try to explore all of them and see which one actually works best. That will do it. Thank you guys. See you in the next video.